Hey everyone, I just wanted to pop in and finish up today's lesson and start off some workbook problems with you. So, we left off yesterday talking about experimental studies, randomization, random number tables, and how we would get those values. So I just want to recap some of these words. So an experimental study is when you're testing a new product for and changing one of the variables to make sure and see if there's any effects. It's important that when you're testing a new product, you're only switching one thing at a time so you can tell if it's effective or not. In addition to using a random sample to get the best results, it's also important. That's just called randomization when we are selecting a sample from a population group for an experimental study. Lastly, it's really important that we are able to replicate the results. Like in our experimental study, if we change something and there were effects, it needs to be something that can be replicated over and over and over again with producing the same results, because the first time it could just be a fluke. So replication is the experimentation on many of the same product rather than just drawing a conclusion from just simply one instance. And when we're doing these experimental studies, it's really important that we have a control group, which is the product and everything is unchanged in it. It's the original state. And we have an experimental group that we're comparing it to, where this is where we have the variable in the altered state, where we're testing to see if the changes had any effects in comparison to the control group. So randomization and replication are used to create these repeatable results. And the control and experimental groups are how we can determine whether or not these results were because of the changes. So, example 3 said, to see how a new product compares to other older models or competitive models, your company decides to conduct an experiment. Specifically, your company is going to make cell phone batteries and is testing the battery life against an older model. So in this situation, we work for a company, we make cell phone batteries, and we want to compare our battery against an older model and see how it is. So how could bias get introduced into this experiment? Well, first of all, something kind of weird going on here is the fact that it's our company is conducting the experiment. That's kind of suspicious for our cell phone batteries against an older model, right? So when our company is conducting the experiment, they probably want desired results. It would be best if we had a third party come in and do this. So it's kind of weird that it's our company doing the experiment. Furthermore, there's already just going to be some bias saying this word older model, right? There's bias in new versus old, right? Like people are going to feel a certain type of way if you say like, oh, this is an older battery, or oh, this is a newer battery. So in order for this experiment to be truly unbiased, the batteries shouldn't have any labels. Nobody should know which battery is which except for the people conducting the experiment. If someone's coming in and checking that out. It's really important to avoid bias because a lot of people are spending a lot of time, energy, money. We want to make sure that this is actually effective and actually going to improve people's lives. So that's important. And if we wanted to design an experiment that avoids bias, we would first want to have like set up our randomized experiment, select random batteries, right? So like maybe we have a randomization of the batteries happening, and then we would definitely want a control group, and which is just like the older batteries versus our experimental, which is like the new batteries. And then once we have those things, we can kind of see what happens, right? Then we can draw conclusions on like which is better, right? So again, just to make sure that we're all good, bias could be introduced just on the research and development since it's the same company. They're going to want it to succeed. Also, some people's jobs could be on the line. And so they're like needing a certain desired result because maybe they're going to get a bonus or whatever. So that's something to consider as well, in addition to just knowing old versus new, your company conducting the experiment, like we stated before. And we would want to avoid bias too. Just number one, to make sure the product actually works. But like, what a waste of time too. You're spending all this time and energy setting up an experiment. And if there's bias there, it's inconclusive. You cannot use that information anymore. So you wasted your money to conduct the experiment and get all of the things. You wasted your time when you could have just spent that towards making the product better, right? And also all of the effort that goes in with it. For our experiment, we randomize it to start, right? Control group versus an experimental group, and then compare how long the battery lasts, the mean battery lives, and that's a best randomized design. So lastly, hypothesis testing is when you make a hypothesis and then perform an experiment and see if it was true. Right? This is where we're going to collect, analyze normally distributed data, right? That means we're going back to our normal curve, and also we're going to go back to z-score, okay? So hypothesis testing is when you take data from a sample and test the assumption about the population. What did we think was going to happen, right? Like in our last example, our hypothesis would have been like, if we make a new battery, the battery life should be better. That's our hypothesis. And then we would test it out in our experiment and then take that data from the control group and from the experiment and compare them and statistically measure if, yes, the new battery has a longer battery life, or no, not really, right? So the whole goal here is to determine what's true, not just from an anecdote, not just from, oh yeah, here's a new battery, hope it's better, right? You want to be sure and be certain. If you're an inventor or someone with a business, you're trying to make money, right? You want to make sure that it's actually true and people aren't like going to return your products or something because you claimed it to be one thing and it turned out to be another. So here's an example where we can use hypothesis testing. So the following data was collected by measuring the heights of Christmas trees on our farm last year. You hypothesize that your new farm layout has increased the height of trees. Okay, so you grow Christmas trees, let's just say, and then you decided to change where you were going to grow the trees. Maybe you thought the soil was going to be different over here, maybe the sunlight was going to be different, right? Out of all of the things, you thought maybe your trees were a little small last year, so this year you were like, I'm going to make one change. I'm going to plant them in different places and see if this is going to affect the height, right? Your hypothesis is if I change the location of my trees may be taller, right? And so now we want to statistically see if that's true. The mean height of this year's crop after you moved it is 195 centimeters. Is there evidence to support our hypothesis testing? So let's start with all of the information that we have. So certainly we know for sure that this year's crop is 195 centimeters, right? So this year is 195. Now I have to look at my picture and see, it doesn't tell me anything about last year in the word problem itself, but we can find a lot of really good information in the picture. So we have our normal distributed curve. We have z equals 0 in the center, right? That is our mean. The mean is always in the center as well. Right? The mean is always in the middle right here. And so we know straight away from this that our mean from last year in general was 177 centimeters, right? Because the mean is in the middle. And we can see that as the standard deviations go, to the right 1, to the right 2, to the right 3, to the left 1, to the left 2, to the left 3, Remember, there's always 3 standard deviations away from the mean under our normal curve. And we can see it went from 177 to 185, 185 to 193, 193 to 201, and vice versa on the left. So even though it doesn't state the mean is in the picture, even though it does not state the standard deviation is in the picture. I could do like 185 minus 177, right? That would be the distance right here between these two. And determine what my standard deviation is going to be. Because remember, we would always add it on the right or subtract it on the left. So we find here that, our standard deviation is 8. Lastly, we're comparing last year's information to this year's information. So our data value that we have, this year's crop is 195. We're comparing this year's crop to last year's, seeing if when we changed the location, did it make a difference? So now that we have all of our information, we can go back and plug it in to our z-score formula, right? Mu, x minus mu over sigma. We know what sigma is. Sigma is 8. Mu is 177. And we also know our data value. I'm going to use yellow. Our data value is 195. That's what we're trying to compare. So we can find our z-score. Z equals x, or 195, minus mu, 177 over 8. Punch this into our calculators. 195 minus 177 divided by 8. That's going to give us 2.25, which is, great, because z-scores are always 2 decimals. So this is the z-score. And if we go to our z-score table, 2.25, which is over here, 2.25, so here's 2.2 right here, 2.20, 2.21, 2.22, 2.23, 2.24, 2.25, we get 0.9878, right? Kind of seeing where 2.2 and 0.5 intersect. It's that number right there, 0.9878. That's the area under the curve to the left, 0.9878. So this gives us a 0.9878, or 98.78% of trees this year are bigger than last year's, right? 98.78. Is that a pretty good number to say that, yeah, I moved my trees and they're larger? Well, yeah, because this is a super large number, right? So now we can, instead of being like, oh yeah, like 195 sounds bigger, we can like use statistical evidence to back up that claim and support our hypothesis. So that's just what this is saying here, interpreting this. And also, it's clear that this new layout has increased the tree heights. The only other option really is like you just so happened to pick an abnormally large batch of your sample and it gave you a larger average, and everything else is actually just the same height or smaller, right? But that's not very likely to happen because it was a random sample, right? But our trees are significantly larger this year in comparison to last. So moving the trees definitely helped. So I'm going to conclude this video and put a separate one for the workbook. I want to work through some of them with you. And so I'm going to assign workbook section 9.1, all of the problems except number 8. And we will work through some of them together. I'll see you in the next video.